Spanish to count and everything else. This number we just nice and spread out. Calculus test last week. Chemistry test next week, and anthropology test week.
Yeah, we didn't have as much time to meet and try to screw our students over this semester, so unfortunately, we need your time. Alright guys, so I want to do a quick couple of things. I got a question on homework already. I want to do... Hey everybody. Who's that? It says that. Hey everybody. Oh, it's like that doctor from Simpsons. I had a voice in my head. Thankfully none of them are telling me to kill anybody. So I want to talk about a to the x, e to the x, trig functions, and then I'm going to let you guys do a little group work thing I talked about yesterday. There's also going to be a quiz.
So after today we should be done with 3.4. Or we already is it 3.4 like 3.4 chain rule?
Chain rule.
Yeah, 3.
Yeah, which that basically is just the derivative of
This is going to be a little weird.
derivative.
132.
Yeah, stuff we're probably going to.
Because today we're going to talk about 3-3, and then we already talked about the chain rule, which is actually 3-4. All right, so let me see. You got a question number 33.1, which looks, like I said, yummy. Now, you got to be real careful when you do this homework. 3.1, we do not know product rule, we do not know quotient rule, we do not know chain rule. Oh, so in 3.1, what's the only thing we know in 3.1 is
Power rule, right?
we just know this.
That's basically the power rule.
So the problem they give us, number 30, now it looks even yummier, is this guy. I say V for some reason. Now, if this was just sitting on a test, what might you use to do this? Chain rule, right? So I wouldn't have to FOIL it out. At least it's not a 7th power up there. That would be really evil. So, first thing I would do...
Well, change the radicals.
Yeah, I'd make them not radicals anymore. Plus...
X 1/3.
Oh,
2/3.
2/3.
What?
Is it 1/3?
It's 1/3 because it's a cube root, and it's negative because it's on the bottom.
Different book, huh?
I thought it was a cube root.
It is a cube root. That's why there's a 3 on the bottom. Right? But it's the first power, right?
Oh, yeah.
Power on the top, root on the bottom. And it's negative just because it's on the bottom. It's flipped. All right, how many those parts? And then, because we're in 3.1, you have to do what? Yeah, FOIL it. So notice how I haven't put a prime yet. Notice how I keep making that point. Like, but I get people all the time, they just put a prime, they're like, all right, now I'm going to start doing something. Well, you haven't taken a derivative. Don't put a prime yet. That'll confuse you and me. All right, so and then the next thing I love,
That becomes X.
Good. I get people telling me X to the 1/4, makes me cry a little bit. Half an X and half an X make a whole X. I like that. That was awesome. And then, that's fine. Normally I'm the only one laughing at my jokes.
X and 1/3.
Yeah, because this would be 3/6
Yeah, so 2X.
minus 2/6, 1/6, and then you get another X to the 1/6, so you get plus
2X.
2X to the 1/6. Alright. Let's let it go. It's alright. And then what happens back here?
X to the negative 2/3.
You guess. Right. And now that should be relatively easy now. That wasn't all that bad, was that?
I just changed it. That was bad.
So now V prime, I do this one.
1 plus 1/3 X to the
Good, because the 1/6 would come down. 2 6 is 1/3.
-5.
X to the,
-5.
yeah, 1 minus 6 is -5. That's awesome.
And -2/3.
Good. The -2/3 comes down. -2 minus 3.
-5/3.
There. Yummy delicious. Yes. Oh, it's kind of creepy.
Oh wait,
Yes.
what's 3.2? Like, what can we use in 3.2?
3-2 product and quotient.
Okay, so we can't use chain.
No.
I'm asking for the test. Well, the quiz.
Well, on a quiz. Yeah, I got you.
So we can't use chain on the quiz.
Can't use chain on the quiz. I'm not going to give you a problem that. Well, we'll see.
71.
All right. 71. This is one of those. It starts sounding like that problem from earlier, but it's not as bad.
Oh, yes, it is.
So they give you, find the parabola with this equation. Maybe it is bad. Let me see. Y equals ax squared plus bx. Where the tangent line has equation y equals 3x minus 2 at 1, 1. So the tangent line at 1, 1 has that equation. It just sounds like the other problem in a way. I don't know if you know what I'm talking about.
Did they already give you your slope?
Yes. Yeah. So what's the slope of the tangent line supposed to be at the point we're interested in?
3.
All right, so the slope's supposed to be 3. And what's the slope of my parabola in general?
2x.
Isn't that so pretty? Well,
You can do it? Yep.
2x plus
2ax
plus b.
plus b. So what's 2ax plus b have to equal?
That's the slope of the parabola.
That is the slope of the parabola everywhere. More formally, that is the slope of the tangent line at every point on that parabola.
Would you put 1 and 1
We just
on
put
the side?
And then would you put it?
Yeah, so at the point 1, 1, so that's why it's a little bit better to have f of x notation, because then you can say f prime at 1 is
It's 2a plus b.
2a plus b. So what's 2a plus b have to equal?
3x minus 2.
Because it has to equal 3, because we know that's the slope that we want. That's plenty. That's enough. There's a lot more to do, but that's a good place to start. So this, by the way, was number 71 in section 3.1. Is that right?
Yes, 3.1.
Yeah. All right. So that does not look familiar. You need to step it up. Right now in homework, you should be getting into 3.2, if not already done with that. Somewhere close to in there, somewhere. Yeah.
Can we do number 38 on 2.1?
Oh, okay. So this is, I'm going to ask you a question like this. Because I already have. Find the equation. Which one is it again?
38.
38. Okay. Find the equation of the tangent line for this curve at 1, 0. Okay. So, what two things do I need for the equation? So the question is find the equation of the tangent line to this curve at that point.
Yeah, so I know you take the derivative.
Yeah, so one thing I need is the slope. Back in algebra, you might get it because it's parallel to some of the line or it's perpendicular to some of the line. Ooh, that was nice. Much better than it could have been. Or it goes through 2 points, so you use y to minus. Now in calculus, you use calculus to get this, so like you said, I can rewrite this, of course, as.
Actually, 1/2.
So what's the derivative?
1/2 x.
Kick ass.
Got messy. Like,
So then I'm going to bring back in F notation because then it can identify, I want the slope at 1. So you plug a 1 in. So you need the slope and you need a point.
It's 1/2.
I've got a point. And then you can plug it into y minus y1, mx minus x1, or mx plus b, and get b. Cool. I want this problem to become easy. Find the equation of the line, of the tangent line, you go, oh good, you just got to take derivatives and then it's algebra. That's it. That's the level that's at. You guys understand?
Yes.
I can't read most of you guys. Okay. So here you get 1 minus 1/2, which is 1/2, like you said. So that is the slope. And I got the point. And now you just got to figure out what b is. Whatever way you want to do that. All right, 2 ways you can do that. 2 equations of a line. So, well, I mean, you can use this guy. So you can plug 1 in for x, 0 in for y, plug 1/2 in for m. Oh, okay.
What's the other one?
Well, the other one's the main one. What's the main equation line?
MX per b.
So then you can plug in 1 for x, 1/2 for m, 0 for y, figure out what b is. But don't circle what b is, put the equation back together, and that's what you circle. The answer is going to be an equation of a line.
Okay, but when you actually put the 1 into the derivative, it... Oh, did you already do that?
Yep.
Wait, where does the negative 1/2 go?
What was 1 minus 1/2? So when you plug a 1 in, what's 1 to any power? 1. 1 times 1/2 is 1/2. 1 minus 1/2 is 1/2.
Oh, so you're saying 1 to the negative 1/2 is just...
Yeah, 1 to any power is 1.
Okay.
That's a beautiful thing about it. You're like, oh, good. It's at 1. Yeah.
So,
Okay. All right. Anything else from homework?
Number 49.
Oh, yeah, cool. 49?
49.
And 3-1?
Yes.
Okay. Boyle's law. Yes.
Isn't that like chemistry?
Dude,
Yeah.
yeah, buddy. When a sample of gas is compressed at a constant pressure, the pressure P of the gas is inversely proportional to the volume V of the gas. Blah, blah. Oh, okay. So this is where you got to remember what inversely proportional means. So the pressure P inversely proportional to the volume V. I'm sorry. Go ahead. So I don't know if you guys remember or even know what this means. You can write sort of an equation. Well, you can write an equation. You're just going to have a third unknown.
Oh, can you guys do?
No. Don't go there. No. You don't have to know any chemistry to be able to do this problem.
And then the P over P.
So P varies inversely.
1 over V.
Good. I like the V over V, but you always have this proportionality constant. So your take-home pay varies directly with the amount of time you worked that week, right? You guys with me? Let me say it again. The amount of money you make in a week varies directly as the amount of time you worked that week. So if you worked more time, but it's not pay equals time, or else if you worked 40 hours, they're like, here's your $40. No, I want to multiply that bad boy by the proportionality constant, which we also know as the wage I'm making, right? $10 an hour or whatever. My first job, I was making $3.15 an hour. I didn't know what to do with all that money. Of course, gas costs like 99 cents a gallon. It makes me feel old. That's why we need this. And that's why in Part A, look at all the shit they tell you in Part A. If you have a book, you can look at it. Part A, they say, the pressure, oh, I understand. Blah, 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 blah. That occupies 0.106 cubic meters. That's not the pressure, the volume. And 25 degrees is 50 kilopascals. So the pressure is 50. And you'll have to actually know the units. The units don't really matter as long as they're consistent. So they tell me the volume. They tell me the pressure. Why do you think they did that?
To find.
Yeah. So it's just like if I said, all right, you make a certain amount per week. Like, okay. Let's say you worked 40 hours and you make $400. Now you can figure out how much money you make per week, right? And then I can ask you, well, what if you work 30 hours? How much can you make? Well, since you figured out how much you make per week, you can now do the next. So K is a big deal. You got to figure out what the hell he is to do anything else. So they have to give me a situation to figure out what K is. Part A, you figure out what K is. And then part B just says calculate dV dP. So that's written incorrectly, right? You guys see what I mean? So let's do this problem. Help me out. Somebody help me out.
You multiply the V over to the other side, so you do dV.
Yeah. So let me just plug it in how we got it. So there's my volume, there's my pressure. How do we get K?
You just
Multiply. It's insane. What's that? Multiply by 100 and then divide by 2. That's a quick way to multiply by 50. 5.3, whatever the hell is. Who really gives a shit? But it would be, I don't know if you guys can see this. It would be cubic meters, kilopascals. Bam. Like foot-pounds. You just multiply them together. Does it really matter? No. If you're in science class, units would rule everything. We're in math class, so numbers are more important. Yes?
So it says write V as a function of P. So
oh, okay, cool.
So you just multiply.
Yeah, so then V equals K over P. That's one of the most beautiful little things about algebra is you can just switch those two.
Okay.
Of course you can, right? 10 equals 20 divided by 2. 2 equals 20 divided by 10. Yay! So you can always just whoop. All right. That's part A. So now I know what's the real formula for V. What's the formula for V?
K over V.
No. V equals 5.3 over P. Cool.
Okay.
See, now we know a little more information. Thankfully, you don't have 3 unknowns. We only have 2. And really 1. Just got to tell me 1 and I know the other one. So in part B, they say calculate dV dP when P is 50. And here's let me see if you guys realize the mistake. So they say calculate, and 2 things here. Now they're bringing this back in, and it kind of makes sense of bringing this back in because we don't have X's and Y's. Prime notation is really reserved for when it's X, just to make everybody aware. If it's either other letters, I want to know, am I doing dP dV or dV dP or what the hell? How's that? Is that cool? And that's why this notation is a little more powerful because it's a little more specific. What I always get is somebody will put a 50 in. So if I put a 50 in, V is like 1/10. And what's the derivative of a number?
0.
0. And then, so everything is 0. No, shit, no. You get the derivative first, and then you plug 50 in. It doesn't make any sense to plug it in first, because then you get a number, and it's always going to be a 0 derivative. That doesn't make any sense. So tell me, what does this mean?
Oh, the derivative of volume.
No, be more physically specific. Don't say the word derivative.
How does V change with respect to P?
Yeah, so as the pressure changes, how will the volume correspondingly change, right? That's one way to look at that. Sort of like your wages are so many dollars per hour. And yes, I did say dollars, like water. So dollars per hour, right? So so my wages can be looked at as my hours change that I've worked. How does my money change that I get, right? Same kind of idea. So how would I get dV dP here? How can I rewrite V first?
E to the negative 1.
Kick ass. Well, what?
Negative 1.
Yeah. And so what would dV dP be?
Negative 5.
Negative 5.3?
T to the negative 2.
Negative 2. Alright. Now real quick. as p changes, well, let's see, it depends on which way it's changing anyway, but it looks like the volume is going to be decreasing, right? Or at least it'll be negative. It'll be decreasing. So now they say find dv dp when p is 50, right? P? Yeah. So now you just got to plug a 50 in for p and see what the hell it is. And then interpret what it is. What units is this in?
ABA.
No?
Meters.
Cubic meters per kilopascal. I don't know if you know pascals, kilopascal. Don't kilopascal. What's wrong with that? Alright, hopefully that's enough for you guys to finish that one out. It's basically done. Shit, Jeff, don't be doing that. Alright, anything else? Alright, good. Let's get back. Alright, so two things I want to do semi-quickly. First, we'll talk about the E dude. And there's a lot of different ways to analyze E. But let me analyze, let's do this. Let's look at just A to the X. Just any A, any base. And do I know what the derivative is? Some of you guys might, but according to class, we don't know what it is yet. Right? So what do I have to do then if I don't know what the derivative is?
The definition.
Yes, the definition. Limit as...
H plus no.
Yeah, we could do that. Well, let me think what would be better. Let's do... Well, X goes to A would suck, right? Because then we got A's all over the damn place. Let's see. Which way do I want to do it? Well, remember we got the two different ways to do it. We can either do H approaches 0, or we can do X goes to something. Let's do H approach 0. It's a little more general. I'm just trying to decide what's the best way. So now what would that look like?
Say X plus H.
Good.
Minus A to X over H.
Okay, cool. Now, can we do anything with this?
No.
Yes.
Oh, the consequence?
No. I love this because people forget this.
A.
What are the X and the H? What are they?
Exponents.
Exponents. And they are adding, which means I must have been doing what? Multiplying like bases to add. So pull it back apart. What was I multiplying to end up at A to the X plus H?
A to the X plus times A to H.
And now what can I do?
Take an A X.
Yes, good.
A to the X.
Oh,
Alright, let me stop there for a second. Now here's where...
Oh, so would you separate the limits? It'll be A to the X as H approaches 0, and then the limit of A to the H minus 1 over H.
Yeah, I mean, this piece is done. That can actually come out because it's not dependent on H. Do you guys see what I mean when I say that?
Yes.
I can take stuff out of the limit if they're not dependent on H, because then the limit doesn't care about it. There's the constant according to what it thinks. So this piece is the weird piece, right? And just to really do this semi-quickly, there's two things I can say about this. One thing is, if you analyze this, what it comes out to be, so that guy could come out, and what this limit turns out to be is ln A, which is weird.
wait, how?
So if we graphed this, if we chose something for A, I'm trying to do this without actually doing, but if you chose A to be 2, and you made a table about it, or you graphed it, and let H get really close to 0, you would see it approaching the what natural log of 2 is, for example. Now, let me back this truck up a little bit. A much better way to look at this, I think the book eventually does, is to look at this piece by itself. This is the piece that's most important to this problem here. If I can figure out what the hell that is, I can figure out, and there supposedly it's natural log of A, right? So this is interesting. I want to know, let's say I want to know when is this thing equal to 1. That would be interesting. If that thing was equal to 1, then the answer here would just be a to the x times 1, right? It would be its own derivative. And this is kind of like what I said at the end of class last time. This, to make this true, we actually define it to be the number e. This is one way where e comes out. E comes out of much more interesting places, but they're based off of the second half of this course. So when we get there, I'll come back and show you a better way to define e. But when you do this limit, if you were to pick different values of a and try to get the limit to get closer to 1, e would be the thing that would make it go to 1. It's really weird. What does that really mean? That means that if I graph e to the x, what's its slope at 0?
2.7.
Yeah, whatever e is actually. So it's like its own slope. Everywhere it's its own value. It's its own derivative. And if I look back here, if I make a e, what's ln of e? 1, right? All right, maybe. There is a really nice, a better proof of this that I haven't done in forever, that I need to look back up. It's kind of nifty the way you manipulate things, so I have to look it back up. Maybe I'll bring it next time. But for right now, what I want you to realize is two things. In general, if you're given this, then its derivative will be a to the x ln a. So for example, if I had f of x equals 3 to the x, its derivative will be 3 to the x ln 3. But what's really nice that comes out of here is if I'm given e to the x, its derivative is e to the x. Done. Because ln of a base is 1. Maybe. And we sort of did this not perfectly the last time, but we saw how it made sense that it's at least close to being its own derivative. The slope was actually already defined by the e function itself. When I'm back here, it's positive but very small, and then it grows, and then it gets bigger positive. So it follows its shape. E is the only base that actually the slope lies right on top of the damn thing. So at 0, the slope would be 1. The slope of the changing line at 0 would be 1 for e to the x. It's kind of nifty.
So at 2 it's 2, 3 is 3, 4.
No. It's e to the x. So what's e to the 0?
1.
That's why it's 1. So at 2 it would be e squared. And so forth. The derivative, the slope of e to the x is equal to itself.
Alright.
So whatever e to the x is at a point. So at 0 it's 1. So the slope of e to the x is 1.
So whatever value we put in the outcome
is also the slope of it. So what is the... now here, I haven't shown you this yet, but let's see. This is kind of silly. So what's g double prime? That's great. What's g triple prime? Now, the reason I'm doing this is because I want to show you, if you get past 3, you just put a little 4 there instead of having like 18 billion little tick marks. Or like you do, and then 5, and then little tallies. That would drive people insane. We just decided this represents the 4th derivative. And of course, you know, if I can do g to the billionth derivative, it's freaking e to the x. It's always itself. Alright. Cool. Yes, sir?
What about e to the 2x?
Oh, good. I like it. So now, the reason we learn product, quotient, chain rule is because we can combine them with the basic rules for functions themselves. So e to the 2x is basically e to the x, but it's got an inside function. So h prime, e to anything is itself, when you took a derivative, right? So it's itself times, yeah, let me write it all out, times the derivative of the inside function. And I real quick, I promised to do something, I forgot to do it yesterday. If I have e to the x, just to show you this, we always use chain rule, always. We always use chain rule, even before we learned about it. You used it correctly, if you did the derivative correctly. Because what's the derivative of e to the x? Times the derivative of the inside function, but what's the derivative of x?
1.
Okay, sweet. That's what I was trying to say. If the inside is really just a linear function of x where the coefficient is 1, we actually would do the chain rule, but we don't have to because it would just be frickin' 1. It doesn't have to be there. But the chain rule doesn't suddenly become active. It's always there. So sometimes I can ignore it when the inside function is just x. Yes?
So if e was raised to like a constant, like let's say it was just e to the 2.
See, now that, you're getting ahead of me. You're going to give something away. But that's why it's a really good question you're asking. So teachers love to do this, and I am a teacher. So what would this be?
Would it be 0?
It would totally be 0 all day long.
Okay.
So if I said h of x equals sine of the square root of pi to the e, and I said, what's h prime? 0, because this whole damn thing is a number. It is very likely an ugly-ass number, poor little thing. But when I take a derivative of a number, it becomes 0.
So let's say there's a full function, like it's e to the x squared plus 2x.
Totally, all day long. All right.
Would the derivative of the entire function come out?
You ready? So no matter what it is, you identify the inside and the outside function, right?
Okay.
So what's the outside function?
What's
the outside function? E. I love it. E to something. So that's the first thing you care about. That's the only thing you care about at first. And how do you take the derivative of e to something?
It's the same.
It's e to that thing. All right. Times
cosine.
Careful. I'm going to keep doing this because it will help you as we learn more rules and as we get more funky functions. It's better to write the rules so you don't forget something on the way, trying to do too much in your head. So it's the e, it's itself, because that's the definition of the derivative of e, times the derivative of the inside function. They each get a term.
But would there be another chain rule? Or like,
but see, I don't. I'm glad you brought that up. I'm glad you brought that up because everybody. I don't have to think ahead about how many links I need. I just add them as I need them. Does that make sense? I don't have to know at the beginning of the problem how many freaking dolls I got nested in this. You guys have seen Russian nesting dolls, right? You open the doll, there's another one. You open the doll, there's another one. You open the doll, there's a freaking other doll. Sorry. So this piece is done. How do I do this derivative?
Cosine.
Yeah, the outside function is cosine. Oh, yeah, sine. So the derivative is cosine. Times 2x. And you see how I was very careful to make sure that 2x is not inside the cosine? You see that? And why do I not have another chain rule? Because this in here didn't have another inside function, right?
Oh, so for chain rules, can we always take out that coefficient all the way?
Yeah. So at the very end, this guy is free to roam, so I'm going to put him here.
So even if I had like 10 chains, then I can always just take that one final chain.
Because what links the chains? What operation? What operation? Multiplication. Yeah, so you can multiply whatever order you want to. Yeah. Yes, sir?
What's the rule called with the e's? I'm writing it down.
So it's the derivative of the exponential function. That's with the a, and the e is a specific example of that. So if I have a to the x, so here, real quick. So the rule is if I have a to the x, the derivative is, remind me?
A times ln a.
Good. And that's why e is its own self, because ln of e is 1. You just turned yourself on, that's neat. So this is an exponential function, so it's the derivative of the exponential function, and then e is a certain base, that is its own derivative. And it's actually not its own separate rule, it follows the same rule. It's just that ln of e happens to be 1.
Okay, so I have polynomial, product rule, quotient rule, chain rule. Which should I write for next one?
Exponential function rule.
Okay.
The EFR. Alright. Now trig functions. What do we know so far?
The derivative of sine is cosine.
Screw Wednesdays, man. Thursdays. And Tuesdays for that matter. Mondays and Wednesdays are word set. We're going to do this next time, maybe. So we know sine x, what's f prime? Cosine x. What about the other way?
Negative sine x.
Yeah, g prime is negative sine x. I like it. We can prove that. The same way we prove this is exactly the same feel for the proof using the limit definition. So that's there, that's there. So how would I do tangent? Yeah, but you
Do the quotient rule, right?
Square.
I like it because tangent is sine over cosine, so I'd use
Their quotient rule.
quotient rule. So h prime, go with me. So what is it?
Times cosine x minus sine x times cosine over cosine x.
So there's the rule, right? Trust me. The people that write the rule out and then do derivatives will make fewer mistakes than the people that don't. It's just a fact of life. A fact of life. So what's the derivative sign?
Cosine x.
Cosine. So you get cosine, cosine.
Cosine squared x. Plus
Derivative cosine.
negative sine.
The negative sign is positive over cosine squared. So you get 1 over cosine squared, which is secant squared. So some of you guys knew that already. Good for you. So derivative of tangent is secant squared.
Oh, because cosine squared plus sine squared is 1.
You got it.
Alright.
Now watch this niftiness. So you can prove all the trig function derivatives very easily. The derivative of cosecant, what would you write it as first? Cosecant. 1 over sine. And then you can use either quotient rule, or you could use sine to the -1 and call it just the power rule, chain rule combination. Right? It would work either way. So here's the neat thing. The derivative of tangent is secant squared. The derivative of cotangent, negative cosecant squared, is neat. All the cos shit becomes negative. Derivative of secant, exactly. And again, how would you prove this? It's 1 over, secant is 1 over cosine, and then you could do quotient rule or whatever. You guys with me? We know the rules to do these things. Everything's based off of sine and cosine, and we know them. This turns out to be, whoever's saying that, secant tangent. Right? Obviously. No, not obviously. You do the work and it comes out.
Are you going to proof for that or not?
Maybe. We'll see if you guys are good. So what do you think the derivative of cosecant is? Negative cosecant cotangent. It's kind of nice, the symmetry. It's nice, especially because you have to memorize all of them. Right? You have to know all of the, the 6 main trig function derivatives. I'm not going to make you memorize the inverse ones. You can do that if you want to when we get there. We're nowhere near there, by the way. We've got to learn a few more things. I heard that. It's the least I could do.
So what's cosecant?
Yeah, what's
Negative cosecant times
I didn't write that down? Oh, sorry. Negative cosecant cotangent. And do you see the symmetry there? Secant is positive secant tangent, so cosecant is negative because it's cosecant cotangent. It's beautiful. Tangent, secant squared, so cotangent is negative cosecant squared. It's beautiful. Sine and cosine, their own thing, they do their own thing. I got time. Look at that. Get your people packing up. Alright, so I'll tell you what. Let me see. Real quick. A couple of these, I'm going to give this to you, and I actually want you to work on this and then bring it with you. And then after the quiz, we'll break up the groups and you can compare answers and we'll see what happens. What?
Quiz on Monday or Tuesday?
Tuesday. Yeah, I'm sorry. So Monday we'll just get into this. So watch this. So if I had, let's see what weird chick I thought you know. All kinds of stuff. Put something. So something not too evil. Yeah, totally. Put interior trig functions. Now here's where I picked this for a reason. This is the one that people mess up the most, secant, because its derivative is a little weird. It's like one function becomes 2. So what the definition or the way the derivative of secant works is it becomes secant stuff, tangent stuff. So the first thing you do is that's definitely the outside function. You have to follow its rule, and then you multiply whatever the hell that is by the inside derivative. right? That's the chain rule. But people mess this one up all the time because it's kind of a weird one. So it's secant stuff tangent stuff times derivative stuff. Because the secant derivative is secant stuff tangent stuff. That's the definition. That's how secant derivative works. Chain rule then says, well, the inside dude gets a term. And of course, that's just 2x, and you can put that out front.
And the same rule applies with cosecant.
Of course, yeah. Just with the negatives on there. So out here, 2x times all that mess in there. Cool. So I really want you to see, once you learn rules, the rules do not give the first shit what the actual function is. So the chain rule says take the derivative of that function, whatever it is, times the derivative of the inside function. So we're going to learn all these different derivatives of functions, but they cannot change the rule. The rule stays the same. It's beautiful if you let it happen. All right, that sounded really cool. All right. That's enough. Let me give you this, sir. And then bring this with you next week. Try to work on this if you can. Yes. On Monday we'll go over this. After you guys get a little chance to have a little community meeting about it.